Here I've got the same piece of wire. The black marks are still right there. And these are a set of ProbeMaster American-made leads. This is gold plating, not that TIN stuff you get from China. Genuine gold plating. We're looking at our Morse, which we know is about 60 milliohms. We got a Hewlett-Packard 34401, 2-wire connection. You see I'm reading something around 1 ohms. It's bouncing all around. I'm not touching the connections, but just, here I am touching them, just wiggling them around causes the resistance to jump all over the place. This meter has provisions for 4-wire measurement. So I have to add 2 leads. Here are the 4 wires connected to the same piece of wire we used before. You see there's the black mark. So we'll just put the wires as close as possible together. And then using the 4-wire ability of the Hewlett-Packard, I'm letting it settle down for a little bit. So with 4 wires coming from the meter, 2 of them are measuring and 2 of them are excitation. And we knew before it was about 0.64 ohms, whatever. In 4-wire measurement, there it is. If you have a meter with the ability to do 4-wire measurements, this is how it's done. Now it's important that these 2 leads be as close together as possible. One way of doing this is to use this kind of a clip. It's called a Kelvin clip. And you would have 2 red wires or 2 black wires, not red and black. In other words, you would have both of these wires. And it's designed that 1 wire is connected to this piece of metal, and the other wire is connected to this piece of metal. So when you clamp an object in there, the excitation current and the sense voltage leads are very close together. They also make a Kelvin connection in a hook, where it's a 2-wire hook. 1 wire here and 1 wire inside that is exposed here at the base of the anvil. They make alligator clips, where the 2 pieces are insulated from each other, and they clamp on so that places the sense and excitation directly as close as you can get them together. Now when you're using one of these, it looks like this, where these are the wires looking on end of the Kelvin clamp. And you see the energizing signal and the sense signal are applied as close as you could possibly get them. There's no better way than to straddle a wire, clamp it. I picked this up somewhere along the line. It has an input-output terminals, a resistor symbol, and two more terminals. And what's in it? Oh, and it's marked 1 ohm, 250 watts. And what's in it? We have a Dale 250 watt 1 ohm resistor, where the red in and out are just jumpered directly, and the black one goes through to the resistor and comes back out. Now they've taken at this terminal up here and the black terminal up here, which are connected to the resistor, they've taken a lead off of there and connected it back to here. What they should have done was taken that lead and put it on these solder terminals here. In other words, to make a true 4-wire connection, we want the sensing, and this would have been the sensing, to be as close to the resistor as possible. This is 1 ohm. We don't know what the resistance of this lead is, and this lead. This was probably used as a current measuring device. You hook your power supply here and your load here, and then measure again 1 amp, 1 ohm. Makes it convenient for calculations. The voltage difference here, or the sense voltage, would be an indication of the current from here to here. And the epitome of this device is this. This is a 0.005 ohm or 5 milliohm resistor with built-in sense leads. So these leads actually connect internally to the ends of the resistor. So these are for current flow, and these are for sensing. Little resistor, 0.005. And looking at it, a 2-wire measurement, we should have another 0 at least there. We're reading 0.46 instead of 0.05. I'll hook up the other 2 test leads to the resistor, and I'll hook the leads up to the Hewlett-Packard. And I'll put it in the 4-wire measuring condition. So there it's settled down and is reading 0.005. So that's the 4-wire measurement on this little resistor. Here's that resistor. The one I had was 3 watts. But you look at the detail of how the wires are made inside. The sense wires, that would be the, well, there they are. The sense wires, sense leads, are embedded as close as they can be to the resistance material. So we've excluded this little wire from measurement. Looks like it goes in, makes a 90-degree bend, and there's a weld here that leads to the resistive element. And these are actually made for 4-terminal, 4-wire measurement. This is a 4-wire diagram, and this is a thermistor. In other words, it's a resistor whose value varies with temperature. And let's say this is 1,000 feet. Back to the current source. And these leads, sun shines on them or they're next to a boiler, and then you turn the boiler off or turn it down. So the resistance in these wires, they're no longer leads, is both significant and variable. So in order to read the temperature, which is done by reading the resistance, it's a 4-wire hookup. There's a current source and a current loop and a voltmeter over here. And these are usually located not together, but in a control room. This could be located out in the factory somewhere. Also looks like this, which is the same thing. Current loop, an RTD, which is a resistance temperature device, and the voltage sensor. These are wire resistance. And the idea of this is to ignore them. So it's not just always measuring with a set of leads and an ohmmeter. Could be an industrial situation where this is extremely remote or inaccessible. And the last I'm going to discuss, but not, there are more. Look at this. We have a power supply driving a load. That's simple enough to understand. We hook the load positive to power supply positive, negative to negative. But what happens, this is a regulated power supply, what happens to the lead resistance once again? Well, instead of measuring the power supply voltage here, it's measured as a set of sense terminals. And there's a shielded small conductor wire sensing the remote voltage and carrying it back to the regulated power supply, which in turn regulates not this voltage, but this voltage. This is just another drawing. Most high-quality regulated power supplies have a jumper, not necessarily a switch, but a jumper that allows the voltage output terminal, in this case the positive, to be sensed locally with no connection here, or by removing that jumper, being sensed remotely here. These wires are typically twisted and maybe shielded because any induced voltage on this will appear at the sense terminals, which will be appear here. Well, sometimes you put a little capacitor across the load to eliminate any time constants that may cause a cyclical variation. If you own a Hewlett-Packard or another high-quality power supply, check the back terminals to see if there's any sensing strapping. Typically, you have to design the system so the drop in the wire from here to here is no more than 1/2 or 3/4 of a volt. With special conditions, you could design it for a much bigger voltage loss. But the typical power supply, Hewlett-Packard, Harrison, Lambda, cannot correct more than 3/4 of a volt drop.